Are you ready to embrace AI? Are you ready to be the agent of change your organization needs in this AI-enabled world? The new wave of AI from the data center to the network and into the edge has arrived. How will your organization adapt to new requirements, models, and faster latency needs? How will your organization cost-effectively add new AI functionality while reducing size, cost, and power? How will your organization source suppliers to provide the longevity needed for you to build and operate your products in the field for years? And how will your organization maximize efficiency so that each one of your AI, software, and hardware developers operate together seamlessly? Change the future with FPGAi.
All right, so why FPGA is good for AI? And first, let's talk about the major use cases and how we see it. As Sandra talked, FPGA is used in many different markets, spanning from data center to wired and wireless communications, to industrial edge, robotics, and many different kinds of embedded applications. With the recent AI breakthroughs, we expect that many of these markets will be either enhanced or disrupted with AI functionality. We don't know which of the machine learning approaches will be useful. Maybe some of them will be deployed successfully, maybe all of them will be successful. But our focus at Altera is to make sure that if you decide to use AI on FPGA, we provide the most power-efficient and cost-effective platform for you to do so. There are different classes of how we can run AI on FPGA. The first class is when actual AI inference runs on FPGA itself. And we want to make sure that in this case, we provide the most power-efficient platform. The next use case for FPGA is where the actual inference kernel does not run on FPGA, but FPGA is used as AI attach use case, when we help other silicon architectures to run AI inference or training more efficiently. For example, on this slide, you can see how FPGA can be used as AI network interface card to help AI-specific data movement patterns. Another use case is when FPGA can be used to pre-process data going into GPU or ASIC accelerator to do inference or training. Nowadays, this particular task is very often done on CPUs, which are not very effective, not cost-effective at this workload. And FPGA can enable substantial power and cost savings. So FPGAs has some foundational architectural advantages over other platforms on running this variety of AI workloads efficiently. On this chart, we're trying to show it qualitatively. On the x-axis, we have different machine learning approaches, spanning from classic machine learning approach such as XGBoost to RNNs, CNNs, and transformers. On the y-axis, we show accelerator efficiency. Notice, not the absolute performance, but efficiency in terms of performance per watt, performance per dollar, or any other efficiency metric you choose. If you build an ASIC to accelerate one specific machine learning approach, let's say RNN, your ASIC will be very efficient running that workload, but if you try to run CNN on RNN accelerator, its efficiency will tank. Therefore, it's quite risky to deploy this kind of ASIC accelerators. They're just not flexible enough, and the field of AI is developing so rapidly that this kind of platforms are very narrow and risky. If you look at GPU trend, they are more general purpose, and they can handle a variety of AI workloads, but the efficiency, they sacrifice efficiency quite significantly because of that. So they're not too efficient on classic machine learning techniques. They are not very efficient on RNNs. And recently, they have been really optimized for convolutional neural networks. Well, LLMs, very often, those are memory bound, and efficiency drops again. The advantage of FPGA AI platform is that due to reconfigurable nature of our architecture, and not just the core, it's in addition to core, we have reconfigurable IOs and memories and serial interfaces. We can handle any neural network architecture with very good efficiency. And as a result, FPGA architecture can adapt to a diverse set of neural architecture requirements. Let's look at a set of recent benchmarks tests we ran. In this particular use case, we're looking at accelerating ResNet 50 inference in a single stream, low batch scenario, which is very common in embedded AI applications. So here we're taking our latest Agilex-5 FPGA with embedded AI tensor block and compare it to devices from AMD, in this case, AMD Versal AI Edge, and NVIDIA's embedded GPU. You can see that for this use case, Agilex-5 can deliver between 50 to 65% higher frames per second than competing solutions. By the way, the reason we picked these particular devices to compare to because they roughly fit the same power envelope of about 20 watts, which is a good fit for many embedded applications. Here's another use case. So we wanted to show this, how we adapt to different parameters of AI networks. And we thought FFT would be a good use case to demonstrate this variety. Another reason we chose FFT is because there's a lot of research proposing to replace some of the layers in CNNs with FFTs. So we took our Agilex-7 FPGA in a lower speed grade and compared to dedicated AI accelerator from AMD AI engine. And we just chose the latest they have, the second AI generation AI engine. And what we did, we swept the parameters for FFT from a 32 lon FFT to 32K lon. We took 11 points and compared relative power efficiency between FPGA and AMD's AI engine. And you can see the results on the chart on the right. Out of 11 data points, in 70% of cases, we deliver high performance per watt. In about 3 cases, we are comparable. And only in 1 case, dedicated ASIC for accelerating AI was slightly better, 20% better than FPGA. So this is just another demonstration of how FPGA architecture naturally adapts to any FFT length, while the fixed VLW architecture is optimized for a very narrow use case. All right, now let's dive in a bit more into architecture of our Agilex-5 FPGA and look at the evolution of FPGAs in general and AI. All right, so this is a high-level floor plan of our latest FPGA, Agilex-5 SoC. At the heart of FPGA is programmable logic, of course. In case of Agilex-5, we feature second-generation HyperFlex fabric with unique programmable interconnect. And it is the first FPGA infused with the tensor blocks. The major components of FPGA core is programmable logic, programmable routing, DSPs with tensor blocks, and programmable memories. The next most important components are IOs. Like everything else in FPGA, those are reprogrammable. In Agilex-5, we offer 2 different types, distinct classes of IOs. One optimized for high voltage, between 1.8 to 3.3 volt standard, and that one is used for such interfaces as I2C, SPI, USB, and many others. And the second type of interface, high-speed I/O, is optimized for memory interfaces or for high-speed general-purpose I/O operated between 1 and 1.2 volts. The next reconfigurable subsystems are transceiver SerDes, located on the left and right of the device. Like everything on FPGA, it's reconfigurable. In Agilex-5, we support more than 40 different protocols with our transceiver PHYs. As well, we have hardened IP for protocols such as Ethernet, and in case of Agilex-5, PCIe Gen 4. On the left corners of the device, we have hardened HPS processor subsystem and secure device manager. HPS in Agilex-5 includes it's a quad core with big little architecture with 2 cores for high performance. Those are ARM A76 cores, and 2 cores for kind of more power efficient workloads. Those are A55s. And in addition to HPS and caches, It also features its own peripheral interfaces, such as USB, TSN, DMA, and others. Secure Device Manager is really where we run our firmware. It's responsible for configuring the device, providing crypto and authentication services, as well as security functions, such as anti-tamper detection. So it's important to know that all these features didn't come and show up in FPGA space at once. They developed over time. So on this chart, I'm tracking the history of FPGA capability over time since the very first very first Altera device. On the y-axis, I'm showing capacity of the biggest FPGA in each generation in terms of logic elements. Just a reminder, in FPGA terminology, logic element is roughly equivalent to a 4-input lookup table coupled with a bypassable register. You can see that Altera's first device roughly featured about 200 logic elements, but it was not true reprogrammable FPGA. Altera's first field reprogrammable FPGA was released with Flex 8000 FPGA in '92. That device featured only programmable logic and routing, and I/O. There were no other components I showed on the previous slide. But just 2 years later, Altera introduced embedded RAM blocks in the FPGA core fabric, and since then, almost every generation featured something new. Stratix line integrated transceivers and hardened DSP blocks in the FPGA fabric. ARIA and Cyclone 5 introduced dual-core ARMs. ARIA 10 hardened FP32. That's extremely important precision for AI, and we'll talk about it more later. And Stratix 10 introduced HBM memory and HyperFlex fabric. And finally, our latest Agilex offering again introduced multiple innovations, such as highest performance DEX and ADCs, NOCs for high bandwidth data memory movement, and AI tensor blocks. So the point of the slide is to show that FPGA architecture is not static. It continuously evolves to serve the emerging needs of emerging applications, and AI will be such workload in the future. Another interesting point on this chart is that I showed only the highest capacity FPGA in a generation, but in reality, the market has a very strong demand for FPGAs of all kinds of capacities. Therefore, we roughly split the segments into 3. The low end, which is going to be covered in Agilex 3 in the latest generation, covering between 10,000 and 100,000 logic elements. Mid-range FPGAs between 100,000 elements to 1 million logic elements, and high-end between 1 million and above. So we expect all of those FPGA domains and markets to have penetration of AI, and AI will be the new emerging workload to drive the evolution of FPGAs. Now, we talked about FPGA evolution, and now let's look at AI evolution. What happened there? So on this chart, I'm plotting the first classic machine learning lane, which got its start somewhere in the 50s and 60s with a Markov decision process and decision trees. Then there was kind of not much development till about 80s with support vector machines and Bayesian networks. And after that, again, there was about 10 or 20 years of not much progress in classic machine learning till XGBoost and DeepQ networks showed up in 2010s. Neural networks developed in parallel. And in fact, biologically inspired neural networks showed up even earlier than classic machine learning techniques. They got it started in the 50s, and then the most popular approach at the time was perceptron, and later followed by multi-layer perceptrons. In the 80s and 90s, we see the development of RNNs and CNNs. And once again, after that period of time, there was not much happening for the next 20 years. Until in 2012, we have a publication of AlexNet. And that paper really triggered an explosion in activity in AI, leading not only to new advanced CNNs, but also new architectures such as GANs and transformers. Just out of curiosity, I'm going to ask the audience, what do you think is the most popular machine learning approach deployed today? Just shout out. CNNs? Any other guesses? Transformers? Nobody said Transformers? All right, so we don't know for sure. Nobody knows. But it is most likely perceptron. And the reason I'm saying that is that every modern CPU with branch predictors includes perceptron as one of the main components for branch prediction. And the reason CPUs deploy perceptrons is because they're extremely small, they consume very little power and space, and they can deliver inference with a nanosecond latency. The point of this chart is to show that AI architecture evolution is accelerating since AlexNet, and we really don't know what's going to be the state of the art in the next 2 to 3 years. And this is the traditional strength of FPGA. Whenever the market is unstable, the workload is not known, and the standards are defined, choose an FPGA. We can always adapt. Here are some of our custom quotes confirming incredible efficiency of Agilex FPGAs on 2 very different classes of machine learning workloads. The first quote is from Thomas Sommers, CEO of Positron, whose demo you can see in the Customer Experience Center, talking about how Agilex FPGAs can deliver up to 3.5 times higher performance per watt and up to 4.5 times higher performance per dollar than leading GPUs. The quote on the right is from our partners at Myrtle AI, who are focusing on extremely low latency inference using different types of neural network architectures. And there, Agilex can deliver microsecond latency inference, which is incredible. And no other silicon platform can deliver it to you today. Speaking of latency, let's look back at this chart about different machine learning approaches. So people think the latest is what's going to be used mostly, but as I said, perceptrons are probably the most widely used neural inference accelerator today. So it just shows you the space and the trade-offs between different models. The models in the upper side of the chart, they are more accurate, but they require a lot more compute, and they have impose very high power and memory constraints on your system. The approaches on the lower side of the chart, they require a lot lower ops, but they can offer you a lot lower latency, a lot lower power, and a lot lower memory. And looking at this spectrum of machine learning approaches, FPGAs are unique in terms of offering you a very scalable platform with the widest range of form factors, package sizes, power envelopes, price points, and supported by the longest lifetime supplies in the industry, anywhere between 15 to 25 to 30 years, and some of our products ship for 40 years. All right, and with that, I would actually like to invite Rob Liston, the founder of Silicon Perception, to talk about a very interesting application of AI on FPGA.
Thank you.
Thank you for coming here.
Thank you, Ilya.
So Rob and his company are doing incredible work with humanoid robots. And I'm very excited to hear how Agilex FPGAs are helping Silicon Perception to push technological boundaries. Rob, tell us a bit more about your application.
Yeah. Let me start with the image on the screen. So on the left, you can see one of our key applications, which is autonomous humanoid robots with dexterous hands. So it's a lot, I know, but these robots, they'll be able to perform everyday tasks with human-level hand-eye coordination. So that requires very low latency.
So tell me about latency
Yeah, latency. Yeah, so actually, on the right, you can see a diagram showing the internal architecture. So what we do to reduce the latency, we run the entire model inside the Agilex fabric itself using compute, DSP, and memory resources. So everything's in the fabric. So we can basically use massively parallel and pipeline data flow execution to achieve the highest resolution, frame rate, and lowest latency anywhere. It's very fast.
Okay, so as you said, for robotics, it requires extremely low latency. So my first question is, how stringent are those latency requirements? And the second is, what's so unique about Altera FPGAs, which allows you to achieve those latency targets?
Yeah. So using Agilex, we can actually run a foundation scale vision backbone at 768 by 768 resolution, 200 frames per second, and 2 milliseconds latency. So it's very fast. So our backbone is a VGG-like CNN. So each layer in the model is actually very different in terms of the memory and compute requirements. It's like all over the map. So the fine-grained resources inside the Agilex fabric allow us to implement each layer optimally.
Okay.
So that's the key.
Sounds good. One of the biggest challenges for FPGA is ease of use. So how do you tackle ease of use challenge, and how do you enable your customers to run FPGA easily?
Yeah, ease of use. We think of ease of use in both a hardware and software perspective. So as a single chip component, our image encoders have low pin count and low power, and programming is just a matter of downloading the weights. And so the memory initialization capabilities come into play. So it's very easy to use, but the real programmability in this type of device is the weights themselves. So what we've done is we've released pre-trained weights for both of our image encoders on Hugging Face. And the models and the weights are MIT licensed open source, so we encourage community support to improve them over time.
Oh, that's great to hear. Another question I have is power efficiency must be extremely critical for humanoid robots like this. So how do Agilex FPGAs help you manage your power budget?
Power is critical. These are battery powered and they need to run for a long time. So one of the things we do is we use the clock tree resources in the Agilex fabric, so we can run each layer in the model at an optimal clock frequency, which saves power.
That's good. Okay, well, it's great stuff. Really exciting work on humanoid robots. We're really looking forward to what's next from you and Silicon Perception.
Great.
Thank you for coming here today.
Thank you. Thank you, Ilya.
All right, so next let's talk about what we're doing on engineering side to make AI to run even better than traditional FPGA. First, let's start with foundational performance per watt scaling. We had great results in Agilex. Agilex Fabric is about 50% faster than prior Strix 10 generation and can deliver anywhere between 30 to 40% lower power, which is an incredible result. But it's not a one-hit wonder. We've been working on scaling performance per watt for many years, and this is what we're trying to show on this chart. It tracks relative performance per watt improvement in Altera FPGAs from Stratix 4 generation to Stratix 5 and on. So the way we measured performance per watt is we took the same RTL, and we have a benchmark suite of 40 to 70 designs, and track performance and power of that benchmark suite through all these generations. So you can see that performance is scaling is very strong. We deliver somewhere between 2x to 2.5x improvements every 8 years, roughly. And the way we achieve it is through multiple means. First of all, of course, we use the latest and greatest process node. Second, we always optimize process recipe for unique needs of FPGAi architecture. We also do a very aggressive design technology co-optimization of our circuits with the process node. And in addition to this, every generation we change both architecture and microarchitecture to introduce new techniques to reduce power and improve performance. Finally, I would like to point out that each dot on this chart shows when each generation was introduced. But if you see that performance and power keep increasing even after initial introduction of the device. And the reason for that is the last bullet point here. We continuously optimize our compiler, our Quartus compiler, and our EDA algorithms to adapt to the new architecture. If you want to find out more details about what we've done specifically in Agilex to improve performance per watt, please attend Mahesh Iyer's talk in one of the sessions where he will describe it in greater detail. So as I said, scaling performance per watt, we have strong foundational scaling, and in Altera we're laser focused to make sure we continue this trend into the future. So performance per watt is great, and it lifts all the boats, whether you run AI or non-AI workloads. Let's see what we do specifically for AI. As Sandra mentioned, we are in Agilex 5, we're industry's first FPGA with integrated AI tensor blocks. Traditionally, computing in FPGAs is done in DSP slices, shown here in purple squares, which are arranged in columns and distributed through the fabric. Conventional DSP usually combines a first-stage multiplier, and will have reconfigurable number multipliers depending on the precision you choose, followed by optional dot product, and then the result can be optionally accumulated with the previous result. The combination of multipliers and accumulators is what's referred to multiply-accumulate, or MAC. So as I said, for different precisions, we have different number of multipliers. In case of FP16 or bfloat 16, we have 2 multipliers per DSP. In Agilex 5, we invented and integrated AI tensor block into the same DSP. So you can reconfigure it to be traditional DSP on the right or new AI tensor block on the left. That new tensor block increased the number of floating point multipliers by 10x compared to conventional DSP architecture. And this allows us to improve compute density significantly. It is important to note that this didn't just show up at once. We also have been working on increasing compute density for FPGA for quite some time. On this chart, we are plotting an increase in FPGA's compute density for floating point computations since Stratix 5 FPGA. So what we're doing here on the y-axis is a log scale in terms of how many MACs per logic element each fabric architecture generation provided. In Stratix 5 FPGA and before, you couldn't really, we didn't have a hardened FP32, and nobody else had. And you had to use about 500 ALMs combined with one DSP for one floating point operation. AlexNet paper was published in 2012, as I mentioned, and just 2-3 years later, we introduced ARIA-10 FPGA with industry's first hardened floating point, 32-bit floating point. And that improved our compute density by almost 4x. In Stratix 10 generation, following ARIA-10, we kept the architecture, but we increased the number of DSP columns in the fabric to give us additional 20 to 30% boost. Agilex 7 was again industry's first FPGA with hardened bfloat 16, floating point 16, and floating point 19 formats for both inference and training, which gave us another additional boost of almost 8x. And finally, AI tensor block, another 10x boost. So if we look at the history of the last 15 years, we have increased compute density on FPGA by an incredible 140 times. So what we're really trying to do is to make sure that compute is never bound in your application, that the compute is almost free, while you still have all the reconfigurability of FPGA. Now, what if your AI application, or any application, is not compute bound? What if it is memory bound? And for those type of workloads, we are offering Agilex 7 M series, which integrates high-speed, high-bandwidth HBM memories, as well as LP5 and DDR5. To move this bandwidth on our FPGAs, we developed a new NOC architecture, which consists of 2 main parts. The horizontal NOC, which moves data laterally across the FPGA to align to the right column, and then the vertical NOC, which delivers data to the final destination in the fabric. In Agilex 7 M series, we're using HBM2E HBM stacks, which deliver a cumulative bandwidth of 6.6 terabits per second. We design our vertical NOCs to make sure we can deliver all of this bandwidth into the FPGA fabric in a hardened manner, in a very power-efficient way, so it doesn't burn any soft logic resources. For horizontal, we size it appropriately because not all the bandwidth needs to go sideways. It will usually get distributed. So we looked at different custom configurations, and we found that 2.8 terabit is the right balance. When we look at our competing device from AMD of FPGA with HBM, we see that their NOC is significantly weaker. It's kind of taps out at 1.1 terabits, and it's not really sized for this workload. It's not very useful for HBM. So Agilex 7 M series provides up to 7x higher NOC bandwidth than our competition for low overhead and very power-efficient data movement in your memory-bound AI applications. All right, I hope I convinced you our silicon is great. What about software? And before talking about what we're doing specifically for AI, let me give you a brief overview of FPGAi software stack. At the base, at the bottom layer, we have device base layer, That layer is not exposed to customers, but it is exposed to our internal tools to be used for optimizations. So that layer consists of device model database, which models slots, programmable routing, DSPs, and so on, and the firmware. The layer above is foundational design entry, which is where traditional FPGA flow is. Consists of two parts again, the quarters, which takes your RTL, your Verilog of HDL, and pushes it through synthesis, place, route, and does all kinds of optimizations. And the second aspect to foundational design entry is embedded software, which can run on our HPS, or it can run in soft Neo cores in the fabric, for example. Above foundational design entry, we have high-level design tools, such as Platform Designer or DSP Builder to auto-generate IP, such as FFTs, or high-level design languages, such as OneAPI, SYCL, or high-level synthesis. Finally, on top, we have various application stacks, which consist of different pre-canned libraries you can use as is, or FPGAi AI Suite or Open FPGA stack to provide application acceleration capabilities. So this stack is, last time we counted, was over 20 million lines of code, probably more now. It's been developed continuously over the last 30 years to enable next generation devices. And we always co-design our software stack with the new architecture. We work very closely between architecture and compiler teams to make sure whatever architectural optimization we introduce will be leveraged by the compiler later. Now, as I said, traditional design flows utilize custom RTL to create the custom IP. It could be combined with embedded software to run on HPS, and customers can use DSP Builder to help them be more efficient with their designs. To help with the AI design flows, we are building, and we're going to demonstrate today to you in all the sessions, a push-button AI design flows with FPGAi AI Suite. So it augments traditional FPGA flow with a way to auto-generate your AI accelerator based on the output from your favorite machine learning frameworks, such as PyTorch or TensorFlow. So FPGAi AI Suite will take your weights, your graph, will combine with your requirements in terms of FPGA capacity or speed that you need, and will auto-generate RTL. That RTL can be easily integrated by you into your main FPGA application. If you want to find out more about FPGAi AI Suite capabilities, please attend one of the sessions where Tim, Andre, and Jim will tell you all about it. All right, to conclude, we talked about how FPGAs are great for AI. They're very unique in the industry in terms of enabling very high application agility due to its architecture. We can enable any machine learning approach with very high efficiency, and this way you can de-risk new AI trends. We have unique platform scalability. We offer industry's highest longevity for our devices, and we offer reconfigurable and flexible I/O. In terms of silicon capability, we have very strong history of foundational performance per watt scaling, and we are focused to continue this into the future. We offer industry's first AI tensor block to make sure compute is never one of your limitations. And we offer HBM and high bandwidth NOC for for memory-bound AI applications. And finally, we're working very hard to enable the best developer usability in the industry by combining best-in-class traditional FPGA flows with Quartus and enabling you to do push-button auto-generation of custom AI accelerators with FPGAi AI Suite. Right. Thank you for listening today. If you want to find out more about all these things in terms of high-performance, low-power FPGAs, single push-button flows with the FPGAi AI Suite, and FPGA agility on all its workloads, please look at this QR code and follow up to the Intel site. These are some details of the configurations and workloads I shared today. A legal disclaimer.
Altera, accelerating innovators.